In this video, I'm going to talk about problem 9 of homework 1. In problem 9, I provide a graph of the metabolic rate of resting Urbs and Dnus, those are make-believe characters, as a function of environmental temperature. The questions I'm asking, though, are about the weight or mass of these two fictional creatures, and the pulse, and the cellular BMR. And none of those things are available if we can't pull other information out of the lecture notes to supplement this data, which is about the metabolic rate of these creatures as a function of their temperature. See, no mass, no pulse, no cellular BMR indicated on this graph. So first, let's take a look at what we can pull from the graph. It says that Kleiber's law is going to be important. And remember that Kleiber's law states that the basal metabolic rate of animals is proportional to their mass to the 3/4 power. So we've got metabolic rate on the y-axis here. We have to pull the basal metabolic rates of these creatures from it. And since you had to do it earlier in the homework, I'm counting on the fact that you can recognize that the Urb has a basal metabolic rate of 60. The Dnu has a basal metabolic rate of 30. And what you need to do then is recognize the fact that that is a 2x relationship. So the proportion, they are to be compared in this way. There's twice as much metabolic rate for the Urb as there is for the Dnu. Okay. So now we have basal metabolic rates, and maybe we can figure out what the relationship of masses is given those metabolic rates. So you can look at the red line. This is Kleiber's original publication graph of his results stating that basal metabolic rate is proportional to mass to the 3/4. And you can see, even if you can't figure it out just from this proportionality, that as mass increases, so does basal metabolic rate. So that the larger the metabolic rate, that indicates a larger mass. And clearly the Urb has the larger metabolic rate than the Dnu. Therefore, the Urb is the bigger animal. Therefore, this question, 2 Urbs weigh less, equal, or more than 1 Dnu, ought to be easy for you, since if this creature weighs more than this creature, 2 of these creatures, oh boy, is that going to weigh more than 1 of those creatures. Okay, the second thing you have to realize is that although this isn't an equality, it tells you something about just how much the difference in BMR will be for any given change in metabolic rate. So if this change in metabolic rate is a doubling, is the mass doubled? Let's look at that graphically. First thing to notice is that, okay, I'm going to pick a spot where the line actually crosses a point we can recognize. Here, at a body weight of 0.1 kilograms, the animal burns 10 kilocalories, but we just say 10 metabolic rate units. If you multiply that mass by 10, you'll find that animals burn not 100, which would be 10x, right? You've gone up in mass 10x. You failed to go up 10x in metabolic rate. We learned earlier in the term, should have anyway, that the cellular metabolic rate, so if metabolic rate is proportional to mass to the 3/4 power, and cell number is proportional to mass to the 1st power, then the cellular basal metabolic rate is proportional to mass to the -1/4 power. So that's cell number. That's organismal BMR. And that's either the mass-specific or the cellular BMR. That means bigger animals have cells that burn less fuel. So any one cell from a larger animal will burn less fuel than a cell from a smaller animal. It tells us that the cell number is a 1-to-1 proportionality with the mass. So if the mass doubles, the cell number doubles. And we said before, if the mass doubles, the basal metabolic rate fails to double. And the reason for that is built into this, because cells of larger animals burn less fuel. So twice of them would burn less than twice the number of smaller animal cells. That's the information you needed to answer that one. And that one. Now, I'll admit I only provided you with the pulse information in the lecture notes, not in lecture. But that information is that pulse also, same for pulse, pulse also has a relationship of proportionality, mass to the -1/4 power. People find this very suspicious. So the bigger the animal, the slower the pulse, but to exactly the same extent that dictates cellular basal metabolic rate. So maybe that pulse is there, maybe the rate at which the heart beats is related to the rate at which individual cells are burning fuel. I think this is all you need to answer that homework problem, but of course, come to office hours or email or use the discussion board if you still have questions.